Hello guys, welcome back to my channel. Today we're going to discuss a very important topic, which is often asked in NEET exam. If you hover through the last year paper that is asked, previous year questions of JEE or NEET, you will definitely see these questions coming in a lot of times. So let's get started with the topic. The topic name is Birch reduction and very famous reaction, Birch and Lindlar's catalyst. So we'll be talking about these two reagents in specific. So I'm basically starting a topic where we're going to discuss about two very important reactions. They have been asked in the previous JEE NEET exam a lot of times. So let's begin with the topic. First, let's talk about Birch reduction. So let's get started with Birch reduction first. Birch reduction. Where do you get it? You get this in class 11th hydrocarbon chapter in the preparation of alkene part. So here the reagent used is sodium and liquid ammonia. Suppose you have this compound CH3, C, triple bond C, CH3. What is it? Yes, it's but2-ine. Now, we basically add hydrogen to it, right? But not in a traditional method. We use it in a different way. So basically, we use sodium in liquid ammonia. Okay, and when they react with each other, we ultimately end up getting a trans product. We get this product as an answer. Now, it may be very difficult for you to digest in the first go, but I'm going to discuss the mechanism right now, which will clear things up for you. So this is but2-ene. And which part of it? Which product is this? Exactly, right? When the similar groups are on the opposite side, the compound is called as trans compounds. Very good. So based on that, the answer should be trans to but2-ene. So we get a trans product whenever we have Birch reduction going on. And that happens in presence of sodium and liquid ammonia. So let's understand the mechanism to see how the reaction actually go like. So let's switch on to the next slide. There we go. Slide number 2. Basically, mechanism starts like this. See, you can also help. Let's participate together. You can see two things are there. One is sodium and the other is ammonia. Tell me, what's a sodium? Sodium is a metal. And being a metal, what will it do? Exactly, lose electron. Very good. We get sodium plus and one electron. Now, what is this electron looking for? Electron is looking for someone who is electrophilic. Excellent. Someone who has a positive charge. So look at this compound here, CH3, C, triple bond C, and a CH3. Now, we are aware that a carbon having 3 triple bonds is sp hybridized. And being sp hybridized, it has H percentage 50%, right? Because see, 50% H, 50% P. And we also know that electronegativity En is proportional to S percentage. So this is the highest percentage of S we can have. So it is the most electronegative carbon we can have, right? Being sp hybridized. So this is sp hybridized carbon. So it is highly electronegative. That means, or there will be a positive charge on it because he wants electrons somehow, right? Now, see, what will electron do? Electron go and attack here. See, it will attack here. Now, how many bonds can carbon have? How many bonds carbon in total carbon can have? 4 bonds. But an electron is attacking there, right? Which is making the number of electrons from 8 to 9. 8 was already there, see? 2, 2, 2, 2. 8 electrons were there. Each bond has 2 electrons. So 8 were already there. I'm attacking another one. So what will happen? 9. It's not stable, right? So this will break. And both the electron of that bond will move to the other carbon, adjacent one. So we end up getting CH3, C, a lone pair. Excellent, a negative charge. Because just keep in mind, if an atom gains a lone pair, it gets a negative charge. And if an atom loses a lone pair, it gets a positive charge. That's it. So double bond, carbon, and this free electron which came in, right? 1 electron and CH3. Now you have studied in class 11th chemical bonding chapter that lone pair repels a lone pair, right? So see here, this is a lone pair. And this is also a kind of lone pair which has some electron cloud. What will happen? They'll start pushing each other, they start repelling each other. So because of the repulsion, they switch their position such that the repulsion is minimized. So there happens an instant switch of position, which makes it look like this. A lone pair here, negative charge suddenly, CH3 and double bond. There's a CH3 here, and this lone pair will come here. Free electron will come here. So the lone pair repulsion makes it to go like this, right? Now, we know ammonia has an acidic character as well because it has an acidic hydrogen, right? So one of these hydrogen will break and this H plus will go to this negative charge. So what do we get then? We basically get carbon. It already had a negative charge, right? So carbon, hydrogen, methyl, double bond, carbon CH3 and a free electron. Now can you guess what may happen next? Yes, exactly. Sodium will lose another electron, see? And that electron will go and attack here, see? Because it needs to be paired, right? And the moment it got paired, it became negative. So we end up getting H, C, CH3, a double bond, CH3, and a lone pair with a negative charge. Now, can you guess what will happen next? Exactly. Another mole of ammonia will produce H plus ion, just the previous, like the previous step. This will go here. And my final answer would be, of course, we will show the flow opposite direction. Yes, because we always show the flow of electrons, right? So electrons will go and attack H plus ion from ammonia. And the ultimate answer will be C, double bond, C, CH3, CH3, H. What is it? A trans product. So the mechanism is not so important, but you have to understand that because of the sodium losing electron, we develop a scenario like this. And because of this scenario, we get a trans product because they repel and they become opposite. This should be a key point for you to remember. So from now onwards, whenever you get a question on Birch reduction, you must get extra cautious and make sure that when you see this reagent, you immediately think of a trans product. So this is what we have to know about Birch reduction in total. Let's go on to the next one, Lindlar's catalyst. So let's go to that part now. Lindlar's catalyst. So basically, we'll be adding hydrogen. We call it as controlled hydrogenation. I could have gone for them. This basically we study under the topic of controlled hydrogenation. Because I'm not getting, see, whenever I add hydrogen to alkyne, I'm expected to get an alkane, but I'm stopping it right in the middle of alkene. That's why it is called as controlled hydrogenation. The next topic is Lindlar's catalyst. So let's study this now. See, we use Lindlar catalyst, as I told you, to have a control reduction. Let me give an example. Suppose I have CH3, C, triple bond C, CH3, and add hydrogen to it in presence of palladium. Just that, nothing else, just palladium, maybe a platinum. We end up getting CH3, CH2, CH2, CH3. We get butane. Starting from but to ine, we end up getting butane. Do you want that? Not really. We don't want butane. We want something else. Lindlar's catalyst, so this reaction is not about getting butane. It's about getting controlled hydrogenation in place. So we use Lindlar's catalyst. This is not Lindlar's catalyst. This is just a random reaction of addition, right? Right. So we'll talk about Lindlar's catalyst in particular. So let me first tell you the problem. Why I cannot control this reaction, which starts from alkyne and go to alkane. The problem is the catalyst is free to work on the way it wants. It is free to work whichever way it wants to. But what we do in Lindlar's catalyst is, in Lindlar's catalyst, we basically use a poison accelerant. So we use palladium, right? We use hydrogen, but we use hydrogen, we use palladium, but this palladium is not the normal one. We basically put some poison in it, such as sulfur or barium sulfate or CaCO3 or quinoline, or these are the things we use basically. What are these reagents? The reagents that I'm marking in green right now, these reagents are excellent. They are poisons. Let me explain the mechanism. It's very interesting. They are poisons. And poison here will not kill anyone, obviously. This poison is basically here to stop its reduction from alkyne to alkene. I'll stop it in the middle. I'll show you how. Take a look. See. In what happens in this reaction, first let me tell you that. So in this reaction, basically, if you have the same product, same reactant, bute to iron, right? The same bute to iron will convert itself to, when you add hydrogen, right, in presence of palladium, carbon, BSO4, or CaCO3, or anything like this, the answer will be CH3, C, double bond, C, CH3. Now, what does it look like? It looks like cis product. So that's cis butene, cis butene, right? Cis butene is the product. Follow my point. This is cis butene. Now, why? Because this addition is syn addition. Syn addition is the other name of same sign addition, right? So let's understand. See, it's like this. Even this reaction is addition, syn addition. Any reaction where we just do hydrogenation is a syn addition. There's no exception here. Syn addition, same. But let's understand why we end up getting alkene instead of alkene. So let's go to the next page and understand that. Okay, moving on. Have a look. Suppose this is a sheet of palladium, and the palladium atoms are arranged in this, right? We know that. Now, what we do is, you will be studying in this hydrogen chapter in class 11th, that palladium, being a D block element, has a very good capacity of trapping hydrogen here in these voids, right? You must be knowing it. They basically trapped it in the interstitials, right? So it kind of, bonds with hydrogen here. Okay, like this. Now, spraying calcium carbonate on it implies, suppose I'm putting calcium carbonate on it, like this, yeah? So this side gets blocked. So this side got blocked totally. There is nothing, no hydrogen that can get trapped there. So tell me, this part is poisoned, right? This part is poisoned. And as it is poisoned with, I can poison it with a powder of barium sulfate, a powder of calcium carbonate, a powder of sulfur, a powder of quinoline. I can do anything, right? And what will this poison do? This poison makes sure, that when you pass, an alkene from this side and this side, and when you pass hydrogen from this side so that they can react with each other, the surface does not provide enough hydrogen to it, right? Previously, if it was providing 100 hydrogen atoms, because of this poisoning, only 50 is available, suppose. So instead of getting an alkane, you'll end up getting an alkene, right? So because of this poisoning, the alkyne stops at alkene, and synodation is because of the normal tendency. So basically, we end up getting a cis product. So this kind of questions have always been asked in exams, and we have to make sure we know it. So I hope you understood the things that we asked. Now let me quickly ask you a question, and then we can wind up this video. So let's get started with the question now. Suppose I ask a question like this. Yes, suppose this is the question that you've been asked. Right? Now, to this, if we add hydrogen in two ways, right? Suppose I'm asking a question based on this in two ways. Palladium, right? Two things that I'm going to ask is, suppose I have palladium hydrogen in presence of BSO4, right? And what about the other one? Let's say I'm giving you a question based on the other guy, sodium and liquid ammonia. Cool. What would be the answer? So you can pause the video, take a minute time and do it. Make sure you use wedge and dash notation to show the product. So pause the video, do it. Okay, welcome back. Let's try to do the question now. See, we know that these reagents cause syn addition, right? They cause syn addition. We are aware of it. So as it causes syn addition, what would be the product? Exactly, the product will be a double bond, right? And where will the hydrogen go? Double bond, and the hydrogen will be both the hydrogen will be on the same side. See, on the wedge or in the dash, because it follows syn addition. So we'll end up getting this product. What is it? Cyclohexene. But yes, in presence of sodium liquid ammonia, what do we have? Birch reduction. And we end up getting, yes, anti-addition. So here, your 1H will be on the wedge, while the other one will be on the dash. So we'll get anti-addition. So this is how a question on this can be done. So this is when we have same side, like H is also on this wedge, like this, they're both on the wedge, or they're on both on the dash. Trans is when we have one cis, one trans, like this. Okay, so that is how it can be understood. So I hope you got my point and this was helpful. So with this, let's conclude the video. If you liked it, do share and subscribe to my channel. Thank you so much.